Welcome to the graphical analysis of general equilibrium economics. Within the perfect competition model, we look at competition across multiple markets. The graphical approach is what we're going to do here. We're going to develop an Edgeworth box and look at three conditions for efficiency using graphs to see general equilibrium. First up, we have to realize that what we're going to do in terms of proving the efficiency of general equilibrium is we're going to prove the Pareto efficiency. A lot of times in practical economics, we use Kaldor-Hicks or cost-benefit efficiency, but we have a different standard in some theoretical models. We have a minimum baseline type of efficiency called Pareto efficiency. Pareto efficiency doesn't work very well in the real world because it's too strict. No one person could be made worse off in situations where we're going to have a Pareto improvement or a move towards Pareto efficient states of the world. But it works really well as a minimum standard for us within a theoretical model. Pareto efficiency means that we have a state of the world in which no one person can be made better off without someone being made worse off. This is commonly used in theoretical tools within economics. It's used in the most famous theorems in welfare economics, like what we're going to show you here. And we're going to use this in theory with just simplified models where we only have a few people within our working model, but we understand that it has applications for us thinking about the real world. The three conditions that must hold in an efficient economy, according to this general equilibrium approach, would be that we have exchange efficiency, input efficiency, and output efficiency. This is just like what you would do with a basic supply and demand model. You would look to see that you have efficiency in demand, that your consumers are consuming efficiently. You would look to see that you have efficiency in supply. You would look to see that your producers are making wise decisions. And then you would look at output efficiency. You would see that these decisions by the consumers and producers line up, that we reach the proper quantity and price within the overall market of the economy. First up will be exchange efficiency. The goal is to see Pareto efficiency in exchange. No consumer can be made better off in their consumption without making someone else worse off in their consumption. In this part of the model, we're going to assume that the products are already produced and just given to the individuals. Then we're going to see, do they come to a Pareto outcome through exchange, given the products already in front of them? We're going to demonstrate this in a two-person, two-good world. But with more advanced math, or with more dimensions graphically, the same logic could apply in a more complex world. We want to see if, in this simple model, given a number of goods, will the consumers come to a Pareto outcome through their exchange process? So we're going to demonstrate this graphically using indifference curves. So here what I have is just two basic indifference curves. Standard setups with goods X and Y on the X and Y axes with two people, person A and person B. We have both of their indifference curves. And what we're going to do is we're going to combine these indifference curves to create an Edgeworth box to try and show efficiency in exchange. The way that we're going to combine these graphs is we're going to kind of pick up the person B's graph and we're going to start to cartwheel it over. Instead of just sliding it on top of person A's graph, we're going to pick it up and we're going to twist or cartwheel person B's indifference curve. We're going to keep moving it, keep tilting it until we're getting it almost all the way flipped over. And then once we get it all the way flipped over, we squish it together and we combine the two. So person B used to have an axis down here in the corner, right? That corner for person B is now right here, right? It's in the top right. And so person B's indifference curve increases as it moves now to the southwest because it's flipped over. It's opposite of what it used to be. Whereas person A's indifference curve still increases to the north and east. Right? So now what's really nice about this is we've combined our indifference curves, and what we can see is we can say, okay, well, given, say, person A, given the product of 10 units of X, right? If we are anywhere along this part of the x-axis here for person A, if we're anywhere here, right? We don't know how many y we have. We could be anywhere up and down in terms of y. But if we're right here at 10 units of x, and that means that, hey, we were given 10 units of x to start with. Well, we also know then that person B has 0 units of x, right? And so there's only 10 given. So if I, person A, have them, then you, person B, don't have them. Likewise, if we knew person A was, say, right here at 4 units of x. Forget how many y, doesn't matter how many y. Well, at that point, at any of those points, right, that means that person B, you, have 6 units of x, right? Or if we move all the way out here, we could be at a point where person A has 0 units of x, right? 0 units of x. That means that person B has 10 units of x. Right? And you could do the exact same thing with the y-axis. So what we're going to end up with is we're going to be at some point on this graph, and it will tell us, okay, of the 10 units of x that were initially distributed, and say of the 20 units of y, how many are given to person X and how many are given to person Y. But all of the units will be distributed. So let's look at an initial distribution here, and we'll look at an initial distribution of 0.1. Given the two indifference curves of the individuals, right, we know we're on those indifference curves. There's an infinite number of indifference curves for person A and an infinite number of indifference curves for person B. Given that we have shown these two indifference curves, it means they're the relevant indifference curves for our situation. And if we're on both of these indifference curves, we're either here at 0.1 or we could be somewhere right here. But we're just going to pick one of these two spots, and so we're going to pick 0.1 down here where we're on both of the individuals' indifference curves. This is not a Pareto efficient state of the world. It is our initial distribution, however. So we give the individuals a non-Pareto efficient state of the world, but we give them an initial distribution. And we give them all of the goods. So the goods are already produced. Do they exchange in such a way that we lead to a Pareto efficient state of the world within this model? Well, given this model, we have 0 transaction costs, we have perfect information, we have consumers that have their indifference curves meeting the assumptions that we need to have, that we have convexity to the origin and more is preferred to less, right? Diminishing marginal utility from consumption, right? All of these standard perfect competition assumptions. Would we get to a Pareto efficient state of the world? Well, we're not at a Pareto efficient state of the world right here at 0.1, and we know we're not because what we could do from this point is we know we could move in such a way that made one person better off without making the other person worse off. There's only 2 people in this world, and so if we can make one of them better off without harming the other, then we're not at a Pareto efficient state of the world. How could we do that? Well, we could imagine from 0.1, we could imagine that person A says, hey, I am willing to give up a little bit of X if person B gives me a whole bunch of Y. Right? So that would be an increase in Y for person A and a decrease in X, right? Which means what? It means that person B is increasing in X, right, and decreasing in Y. Right? And person B is willing to do this. How do we know that person B is willing to make this exchange? Well, person B, right, what happens? If they move from 0.1 to 0.2, if we look at person B, they are no worse off. They're willing to make this exchange because they would be indifferent between these 2 points, between 0.1 and 0.2. Person B stays on the same indifference curve. They're not harmed at all. But person A jumps out, right, goes to a further out indifference curve. So person A has increased their utility. So person A is made better off and person B is not made worse off. Therefore, we know 0.1 was not a Pareto efficient state of the world because we could make one person better off without making the other person worse off. So we've made a Pareto improvement as we move from point 1 to point 2. Now the question becomes, is point 2 a Pareto efficient state of the world? And the answer is yes. When we have a tangency between the two indifference curves, we have a Pareto efficient state of the world. When the slope of person A's indifference curve is just equal to the slope of person B's indifference curve, and we have a point of tangency, then there's no way to make one person better off without making the other person worse off. If somehow we were going to move person A out slightly, right? If we're going to move them out, then what we would have to do to be at some point here that person A could be at is we would have to move back person B's indifference curve, right? Person B's indifference curve would have to shift back somewhat. And that means person B is being made worse off, right? The only way to make someone better off without making someone worse off is we can't, right? We can't do it. So we have Pareto efficiency then, right? The only way to do it is to make someone worse off, right? So if we tried to make person B better off by moving their indifference curve off, what happens from IA2, right? That has to shift back. They have to be made worse off. So whenever we have this tangency, we have a Pareto efficient state of the world. This is a Pareto optimal point where we have a Pareto efficient state of the world whenever there's this tangency and the slopes of the two indifference curves are equal. We could also imagine a different Pareto efficient state of the world arising from the initial distribution of point 1. We could imagine instead a different trade ratio here where person A gives up a little bit of X and only gets a little bit of Y in return, right? And person B then is doing what? Person B, right, sees a decrease in their Y, but an increase, quite solid increase in their X, right? We could see this exchange taking place. Well, would person B take this trade? For sure, person B would take this trade. Their indifference curve is moving further out from the origin. So person B is quite happy. Person A remains along their indifference curve, and so person A is indifferent. So what have we done? We've made one person better off, person B, right? Without making someone else worse off. Person A has remained right along their indifference curve here. We could also imagine a situation from the initial distribution of point 1 where it's not just that we increase the utility of one person without harming the other by just leaving them on their original indifference curve, but we could imagine a change from the initial distribution of point 1 to a situation where both people are made better off. We can show this by point 4 here. We could make an exchange such that person A gives up a little bit of X in return for some Y, and we end up at point 4. Now, how is point 4 a Pareto improvement from point 1? Well, both person A's indifference curve moved out and person B's indifference curve moved out. So both of them have increased their utility in this case as both of their indifference curves have moved out. They've moved out in this case such that both of their indifference curves have the same slope and there is a point of tangency, and so we have a Pareto efficient state of the world. There's many more potential Pareto efficient states of the world between the initial points that we drew up. We drew up a point 2 where we stayed on person B's indifference curve. We drew up a point 3 where we stayed directly on person A's indifference curve and person B was made better off. Here we showed kind of splitting the difference. But there could be other points in between these where person A is helped a little bit more than person B, or vice versa. There could be a bunch of these different points. As long as there is a tangency there, as long as the slopes of the indifference curves are equal and we have a point of tangency, we know that we're at a Pareto efficient state of the world. Anytime, anywhere we move from point 1 inside that slit, inside this shaded in region here, right, we know we have made a Pareto improvement. We've made at least one person better off without harming the other person. We haven't moved backwards for either of the indifference curves if we move in this area. But that doesn't mean we're at a Pareto efficient state of the world. We're only at a Pareto efficient state of the world if we end up at a point of tangency. So here we can show all of the potential points of tangency. We note them as points 2, 3, and 4 that we showed previously. However, we also note that there's other points kind of connecting those dots that could exist that we could go through and show. And all of those points, those potential Pareto efficient states of the world, we call our contract curve when we connect them all. Now, there is not just one Pareto efficient state of the world. And sometimes people get a little confused with this because we want to say, this is the Pareto efficient state of the world. This is the optimal point, right? But that is confusing the idea of Pareto efficiency with Kaldor-Hicks efficiency. Kaldor-Hicks efficiency is saying, this is maximizing the value of our social resources, this point right here. That is not what Pareto efficiency is. Pareto efficiency just means we're at a point in such that we cannot make one person better off without making someone worse off. All of these points along this contract curve meet that requirement. So all of those points, any of those points there, they're representing situations where we have a tangency of the indifference curves, where we have the same slopes of the indifference curve, and we're in a situation where if one of the indifference curves is going to move further out, it means the other one has to move back. So we're at a Pareto efficient state of the world. So all of these points along the contract curve create what we call the contract curve for the consumers. So what we get from this consumer model is a situation where we have consumers' efficiency. We have this exchange efficiency. Given the production to the consumers and having some initial distribution, we will not stop until we have taken advantage of all the potential Pareto improvements. There would be no reason having an agent who has perfect information, zero transaction costs, and having more is preferred to less, to leave a Pareto improvement on the table, so to speak. There's no $20 bills on the sidewalk. The individuals would exchange with one another until they reached a point of tangency. A point of tangency would be such that the marginal rates of substitution would be equal to each other. This is simply stating that the slopes of the indifference curves are equal to each other. The marginal rate of substitution for person A is the slope of the indifference curve for person A. So we have the slopes of the indifference curves being equal. We have exchange efficiency, the marginal rates of substitution being equal to one another, and thus we have this exchange efficiency. Next up, we have input efficiency. This is part 2 of our 3 parts of general equilibrium's efficiency conditions. Here, what we're going to have is we're going to have the same analysis, basically, as the exchange efficiency model, but now we're doing it on the production side of things. So now, instead of being given the production, we're saying, do we make the production in the first place in an efficient manner? Do we use resources efficiently to get that level of production? Again, we're going to simplify things down within this model and demonstrate this input efficiency within a 2-company, 2-input world. The goal is to show Pareto efficiency in the use of inputs. Inputs are allocated in such a way that making a higher quantity of one good means a smaller quantity of the other good. We're going to show this not with indifference curves, but a special type of indifference curve with an isoquant. An isoquant is a contour line drawn through the set of points at which the same quantity of output is produced while changing the quantities of 2 or more inputs. It's really just like an indifference curve, but it's saying, instead of how much utility do we get, are we better off, how much production do we get, right? And instead of saying how much utility do I get between 2 goods, X and Y, it's saying how much production do I get, what quantity of production do I get when I combine 2 inputs in different ways. Instead of goods X and Y, now I'm going to look at 2 inputs like capital and labor, right? So we're producing goods with firm X, and we're going to be producing goods with firm Y, and we're going to look at these following graphs to see if they can kind of match up with what we recently did with the consumer exchange efficiency when we get to the last step with output efficiency. So here we look at input efficiency, and we're going to do basically exactly the same thing that we did with exchange efficiency. We start with two kind of basic setups of like indifference curves, but here we have isoquants with the person or the firm X here producing, and their isoquant tells us, hey, at any of these points along this isoquant, we produce a certain quantity of good X. And firm Y is saying, hey, at any points along our isoquant, we produce a certain quantity of good Y. And what it means is that, hey, if you give me a whole bunch of labor, say, but very little capital, right? I have very little capital here. I could produce good Y. I could produce digging a hole, right? If you give me a couple of shovels and a whole bunch of men, I could dig a really big hole. Or you could, somewhere down here, you could give me a lot of capital, right? And just a little bit of labor, a few guys, right? If you gave me just little bit of labor, a few guys, I could also dig a hole. So if you gave me like a backhoe and a couple of guys to run it, I could dig that same hole. And I could create the same number of holes given a few shovels and a bunch of guys, right? Or a backhoe and just a couple of guys, right? I can do the same amount of production of digging holes at any point along this isoquant. Well, if I take firm Y's isoquant and I cartwheel it onto firm X's isoquant, we can think about, okay, if we had some initial distribution of labor and capital, say, 0.1 here, right? Do we end up with input efficiency? Well, given this situation, we know this is not a Pareto efficient point within the production of goods X and Y. And so what we could see is that these firms, just like in the exchange efficiency example, could exchange from this point. They wouldn't stay here if they had perfect information. More was preferred to less. They had, decreasing returns from their inputs, and there was zero transaction costs. Firm X could simply say, hey, right, why don't we exchange to this point right here, point 2, which could make me better off, right? I could produce more units. This is at a higher quantity than I was at before, but you're no worse off. You're still producing at the same quantity. Why not move out to here? And likewise, we could go until we had a tangency between those two curves, between our two isoquant curves. And at that tangency, we would have a Pareto efficient state of the world for our input efficiency. There would be no way to make one firm better off without harming the other firm. From this initial 0.1, we could also move out to, just like we did before, something like 0.3, where we could say, oh, there's just a tangency right there. In this case, firm Y is producing more units, whereas firm X is not harmed from this exchange of the inputs between labor and capital, right? Trading, swapping some labor. So firm X could move back some in labor, but could increase up to 0.3 in terms of its capital, right? Firm X is indifferent between those two situations, 0.1 and 0.3, whereas firm Y is made better off. They can produce a higher quantity at 0.3, and so firm Y would want to do this. At these 2 points where we have this tangency, we could say we have a Pareto efficient state of the world, because from that, moving forward from that point, there's no way to make one firm better off without making the other firm worse off and having a lower quantity. And then obviously we could do just as we did before with exchange efficiency. We could come up with some point where both firms increase their quantity of output by exchanging the inputs that they are using. So what we get from this is the production contract curve. We get all of the Pareto efficient states of the world in terms of using our inputs as those points that we map out, points 2, 3, 4, and all of the points kind of in between, given some initial distribution like 0.1 down here, right? We will end up on a production contract curve. We will end up where the isoquants have the same slope. Where the isoquants are just tangent to one another, we will have a Pareto efficient state of the world in terms of using our inputs. We will be on the production contract curve. At these points where the isoquants are tangent to one another, what we have is we have the marginal rate of technical substitution for firm X being equal to the marginal rate of technical substitution for firm Y. The marginal rate of technical substitution is simply the slope of the isoquant. If you look at the slope of the isoquant, what it is it's showing us the rate at which a firm can trade the x-axis input, say labor, for the y-axis input, capital, holding output, our quantity, constant, or staying on that isoquant, right? The rate at which a firm could trade, say labor in this case, for capital, holding output constant, staying on that isoquant line, right? We're looking at the slope of that isoquant, the slope of that indifference curve for using our inputs and staying at the same quantity. So we're saying the slope of these two will be the same. The slope, the marginal rate of technical substitution for firm X will be the same as the slope, the marginal rate of technical substitution for firm Y, at all of those points on our production contract curve. Just like our marginal rates of substitution had to be equal with exchange efficiency, with input efficiency, our marginal rates of technical substitution have to be equal to one another. The two isoquants will have a tangency on that production contract curve. Whenever we have a tangency and we end up on that production contract curve, we know that we have the marginal rates of technical substitution being equal to each other. The production contract curve contains all the efficient allocations of inputs across producers. At these points, no firm can be made better off without another firm being made worse off. So we've achieved Pareto efficiency in the use of our inputs. Inputs are allocated in such a way that making a higher quantity of one good means a smaller quantity of the other good. Next up is the third and final leg of the three conditions for efficiency in general equilibrium. We have output efficiency. The mix and amount of goods that the economy produces cannot be changed without making some consumer or producer worse off when we have output efficiency. That's the standard of Pareto efficiency for this last group here. The mix and amount of goods that the economy produces cannot be changed without making some consumer or producer worse off. In other words, we can't harm someone. We have to be at a state of the world where the only way to make one person better off, consumer or producer, is to make someone else worse off, consumer or producer. In other words, the production side lines up with the preferences from the consumption side. The trade-offs on the production and consumption side are equal. So our graphs for this will be the production contract curve moving to a production possibilities frontier or production possibilities curve. What we do is we take all of the various points on our production contract curve that we just drew up. And so before we just drew up, say, points 2, 3, and 4, and they were just here. What those involved were from some isoquants, right, from this point 1, they were within this region here. They were within our isoquants, right? We just showed those ones from some initial allocation like point 1. But we could imagine different initial allocations of the capital and labor. We could imagine different point 1s and having exchange from those points, and we would have different elements of the production contract curve. If we did all of the initial distribution points such that we got every production contract curve that we could get some line all the way through our Edgeworth box of use of inputs, right? And so this would be our production contract curve for all of the potential initial distributions that we could have. What we can do from this is we can create our production possibilities frontier. So we take our input efficiency production contract curve and we create the production possibilities frontier for our society. Consider here point T. If we look at this point T, what does that mean? It means that company X has 0 capital and 0 labor. So we are going to be able to produce 0 units of X, right? But company Y has the most labor it can have and the most capital it can have. So we will produce the most possible amount of Y that we can within this country, right? Or within this setup that we have, right? Within our world of 2 goods, 2 consumers, 2 firms, right? Firm Y is producing the most that they could possibly produce. And so what we could do is we could say, okay, well, then company X on this axis here is producing 0, but company Y, their output is as high as it can possibly be. So we measure that or put that in there as point T. Then what we can do is we can move, say, somewhere else along the production contract curve to point U. We've moved back just a little bit. What happens here? Well, good X can produce a little bit. They have a little bit of labor, a little bit of capital. And firm Y can produce a lot, but not quite as much as point T, right? So firm Y, what's going to happen to firm Y as we move from T to U? Well, firm Y has to decrease a little bit, and firm X has to increase a little bit. So we get some point like point U here. And then we could continue to map these things out. We could go to the other extreme and look at point W. At point W, X is producing the most it could possibly produce. It has all the labor and all the capital of the world. And firm Y has none. And so firm Y, they're not going to be able to produce anything, right? Firm Y is not going to be able to produce anything, whereas firm X, they're going to be able to produce the most that they possibly can. So point W would end up as some point like this on our production possibilities frontier. Right? And then we could go to some middling point like point V where, okay, Y can produce some, X can produce some, right? And that's what we see here. We get some X and we get some Y and we get a point V here. If we connected all of the points along our production contract curve, if we connected all of those points and mapped them over to here, we would get our entire production possibilities frontier shown by that curve there, right? So if we map all of these points, T, U, V, W, and all of the points in between, we get that production possibilities frontier as we've shown here. The slope of the production possibilities frontier is referred to as the MRT, the marginal rate of transformation. The MRT is the trade-off between the production of any goods on the market. So in our case, the trade-off between goods X and Y. For every X that we are going to create, how many Y do we have to give up? So what we're going to do next is we're going to take the production possibilities frontier that we just created from taking the mapping of the production contract curve, and we're going to see if that production maps up with our exchange efficiency. Does it meet up? Does it pair up with our consumption decisions? So do our production decisions align with our consumption decisions? And what we can do is we can take either of the consumers' indifference curve and place it on the production possibilities frontier map. Where the two touch is where we would be consuming. And if they touch at a point of tangency, as shown here, we would be at a point of optimality. Here, the slope of the production possibilities frontier, the marginal rate of transformation, is equal to the slope of our consumers' indifference curve. Note, either of our consumers could be placed here, the marginal rate of substitution of person A or the marginal rate of substitution of person B. Why? Because we know that those two will be the same due to our explanation of exchange efficiency. So as long as one of them maps up, they both map up. So we're looking to see if the slope of our indifference curve, the marginal rate of substitution, is equal to the slope of our production possibilities frontier, the marginal rate of transformation. If we have a point of tangency, these two are equal, and we would have a point of output efficiency. If we do not have a point of output efficiency, it would make sense for either the producers or consumers to change the mix of what they are consuming and producing such that we end up at a output efficient point. They would be leaving opportunities on the table. What we can do is we can show this basic condition here, that we have this point of tangency. The consumer's quantities from their exchange efficiency can line up with the producer's quantities from their input efficiency and give us output efficiency. Within this model, this will take place. Producer input efficiency is shown on the production contract curve, which is represented by the production possibilities frontier that we have drawn here. The price ratio must also equal the marginal costs of production. And so what we end up with is we end up with an extreme set of conditions where in efficiency, when we have this output efficiency, everything ends up equaling everything else. What we end up with is a situation where the marginal rate of transformation, the slope of the production possibilities frontier, is equal to the marginal rate of substitution, the slope of the indifference curves. And we know that the slope of the indifference curves has to be equal to the ratio of the goods prices, right? From our intro to indifference curves material, we know that the marginal rate of substitution of A must be equal to the price ratio, right? The price of X over the price of Y. That's our overall consumer equilibrium idea. The marginal rate of substitution has to equal this price ratio. And we also know that this is equal to the ratio of the marginal costs of production. In perfect competition, we get these price equals marginal cost conditions. So the long story short of this is that the marginal rates of substitution will be equal to each other. The marginal rates of technical substitution will be equal to each other. And the marginal rate of transformation will be equal to the marginal rate of substitution, i.e. output efficiency. Saying that we have output efficiency implies the marginal rate of transformation is equal to the marginal rate of substitution. This is the same as saying that it equates the ratio of consumers' marginal utilities of goods to the marginal costs of producing those goods. We get this overall efficiency in consumers, producers, and the entire market. We have reached our three conditions of general equilibrium. We have exchange efficiency, input efficiency, and output efficiency.